So in today's video, we're looking at acid-base indicators. We're going to examine different acid-base indicators and then try to interpret what's happening using Le Chatelier's principle. We're also going to use acid-base indicators to estimate the pH of various solutions. So an acid-base indicator, it can sometimes appear like magic when they change color in front of you, but acid-base indicators are basically just weak acids. They're a weak acid with an acid form and a conjugate base form, like all acids. But the key with acid-base indicators is that the acid version of the compound has one color, while the conjugate base version of the same compound has a different color, a noticeably different color. Most acid-base indicators are monoprotic weak acids, so there's only one color change that will occur. Some of them are diprotic, and you'll see more than one color change, or triprotic as well. So in this little table, we see some common acid-base indicators. We see litmus, something that most elementary school or middle school students have heard of. They know that if you put litmus paper that is blue into an acid, it turns red. If you take litmus paper that starts off red and dip it in a base, it turns blue. So the acid version of litmus is red, while the conjugate base version of litmus is blue. We're going to represent the indicator as HIN, so its conjugate base would be IN-. I've got two little petri dishes here with hydrochloric acid, sodium hydroxide. Hydrochloric acid is a strong acid, and it's in this little dish. It's 0.1 molarity, so it's reasonably concentrated. I've got some red litmus paper. I've taken out a couple of pieces, and I've got some blue litmus paper. I've taken out some pieces as well. Litmus paper is simply a piece of filter paper that has litmus soaked into it. The red version has the acid form of litmus soaked into it. That's why it starts off red colored. The blue litmus paper has the conjugate base version of litmus soaked into it, so it starts off with a blue color. Now notice if you take red litmus, we said that that's the acid version of litmus, and we dip it into an acid. What's going to happen? So let's dip the red litmus directly into the acid. It gets wet, but nothing interesting really happens. If we take the red litmus and dip it into the base, what will happen? We'll put that into the base, and I think you can see in the video the red litmus is turned blue in that base. So red litmus turned blue, but in a base, red litmus didn't do anything in an acid. It stayed red. If you take blue litmus, take a piece of the blue litmus paper here, if I can grasp one. If I take the blue litmus paper and I put it into the base, the sodium hydroxide, so I'm taking paper that already has the basic version of litmus, and I'm dipping it into the basic solution. Nothing interesting happens. It stays blue. But if I take the blue litmus paper with the basic version of litmus and I put it into the acid, then it turns red, or it turns pinkish, right? So we can see litmus is changing color. The acid version of the litmus turns into the base version, so that means a pink becomes blue, or the base version turns into the acid version, the blue turns pink. All right, so there's very common acid-base indicator. As I said, elementary school or middle school students have used litmus before. So, okay. There are other acid-base indicators. Phenolphthalein is a very common one that's used in high school chemistry. Its acid version, HIN, is colorless, and its base version, IN-, is pink. So with phenolphthalein, you'll see a change in color from colorless to pink, or from pink to colorless. Methyl red, it starts off red in its acid form, and it turns yellow in its base form. Bromothymol blue starts off yellow in an acid form, and becomes blue in its base form. Now notice if you had a mixture of those two, if you had a solution with roughly equal amounts of the acid version and the base version of bromothymol blue, it would look green because you'd have a mixture of yellow and blue together. Phenolphthalein is another indicator. Its acid version is colorless, but its conjugate base version is blue. Okay? Now, acid-base indicators are just like any other acids. When you put them in water, they react with water, and they produce hydronium ions and their conjugate base, ion minus. So just like any other weak acid, there's an equilibrium. And so you could write an equilibrium expression for that reaction. It's shown down below. So K indicator, we'll just use that symbol to represent the equilibrium constant for that reaction. The equilibrium constant for the indicator would be the concentration of hydronium times the concentration of the conjugate base divided by the concentration of the indicator in the solution. We only include the aqueous species in the equilibrium expression. Notice, though, in that equilibrium expression that if you had a solution with equal amounts, or very close to equal amounts, of HIN and IN minus, so the acid and the conjugate base version were mixed together in roughly equal amounts in the solution, then they would cancel out in this equilibrium expression, and that would leave you with the equilibrium constant for the indicator equals the hydronium concentration in the solution. That's when you have equal amounts of the acid and base version of the indicator in the solution. Well, if you took the negative log of both sides of that equation, you could say that the pK for the indicator would equal the pH of the solution at that point. So when you have pH equals to pK, you have roughly equal amounts of the acid and the base version, and that's where you'll see a color change occur. Your eye will detect a color change as the concentrations are roughly equal. When you have a lot of the acid and very little of the base, your eye will see the color of the acid. If you have lots of base and very little acid, your eye will see the color of the base. But when they're in roughly equal concentrations, that's where your eye will detect a color change occurring. So the color change will occur when the pH of a solution is roughly equal to the pK for the indicator. Now, I've got here another little petri dish. This time I've filled it with some bromothymol blue, and it's dissolved in water. And so this equilibrium up here is occurring. Bromothymol blue in the acid version is yellow. Bromothymol blue in the base version is blue. And as we mentioned earlier, if you had roughly equal amounts of those in your solution, you'd see a mixture of yellow and blue. You'd see a green color. And from what we just discussed, if you see the green color, then you can know the pH of that solution must be close to the pK for the indicator for bromothymol blue, because at that point you have equal amounts, roughly, of the acid and base version. Now let's see what happens to this dish of bromothymol blue if we start stressing the equilibrium. Okay, so we're going to apply some Le Chatelier's principle to this. Bromothymol, we know the solution starts off at equilibrium because the color in the dish is constant. The color is not changing. You can also tell from the blue color that the equilibrium above has been shifted right now in this dish towards the right. So right now in this dish, because we see blue, there must be lots of the conjugate base for bromothymol blue and very little of the conjugate acid. Now what should I do if I want to, well actually we'll reverse this. Look at the table down below. So we're going to disturb this equilibrium. We're going to add some hydronium ions. I'm going to use the hydrochloric acid that we talked about earlier from the dish down below, 0.1 molar hydrochloric acid. We're going to use that as a source of hydronium ions. Look at the reaction above. Use your knowledge of Le Chatelier's principle, either from a kinetics perspective, forward versus reverse rates, or think about the reaction quotient. You can use the equilibrium expression right here. Try to predict what would happen to the color in the dish if I were to add hydronium ions to the dish. Would it get darker blue? Would it turn greenish and eventually yellow? Predict the direction of the shift if we were to add hydronium. Pause and see if you can do that. All right, let's test your prediction. So I've got the petri dish here. I'm going to squirt up with a pipette some of the acid, and let's add some hydronium ions to this dish with the blue bromothymol blue. Just as I start to add it, I think you can see in the video, wherever the acid's being added, there's a color change occurring. And as I add more acid, we'll squirt out the extra acid there, it is turning yellow. Okay, so now we have added hydronium, and that caused this equilibrium to turn yellow. The dish turned yellow. So which direction did that equilibrium shift? It shifted backwards, and hopefully that's what you predicted using Le Chatelier's principle. If you increase the hydronium concentration by adding HCl, the reaction quotient would have increased. That meant Q would have been larger than K. There's no temperature change, so K stayed the same. If Q is bigger than K, there was a reverse shift in the equilibrium. The blue solution turned yellow. Now, can we shift it the other direction? Okay. So see if you can predict what happens to the equilibrium if we were to add hydroxide ions. We're going to use the sodium hydroxide as our source of hydroxide ions. Now at first that may confuse you when you look at the balanced equation because there are no hydroxide ions in the equilibrium above. But remember that hydroxide ions, OH-, will react extensively with hydronium ions. When you put hydroxides and hydroniums together, you create water, and that reaction has a huge equilibrium constant. So adding hydroxide ions effectively removes hydronium from the equilibrium. So with that in mind, can you explain what would happen if we were to add hydroxide ions to this equilibrium? Okay, so if hydroxide ions react with the hydronium, they're going to reduce the hydronium's concentration in the dish. So reducing the hydronium concentration would cause Q to get smaller, since hydronium's concentration is in the numerator. If Q gets smaller, K didn't change. We're not changing temperature. Q is now less than Kc, and there would be a forward shift in equilibrium, and we should see the color turn from yellow back to blue. So I'm going to take some sodium hydroxide in a clean pipette. I'm going to start adding it to the dish, and I'll add it one drop at a time. So there I've added one drop of the sodium hydroxide. Now remember, these are equal concentrations. The one drop, there was an instantaneous color change to blue, but then as I mixed, it disappeared. So there's a couple more drops. So you can see that the equilibrium is shifting, but then as I mix it, it seems to shift backwards again. Let me keep adding them. There's 2 drops I'm adding at a time. We mix. Okay, it's still staying yellow. The equilibrium is shifting in the region where the drops are mixing, but then as we mix, the equilibrium goes back towards the yellow. So keep adding. Oops, there's 3 or 4 drops there. Let's see if that helps. Okay, so we're getting, what we're doing here is actually referred to as an acid-base titration. If we were doing this with a fancy device called a burette, measuring the volume super accurately, we're basically performing a titration here. We're neutralizing the acid and base by mixing them together. So that was one more drop, and look at that. As I mix, I hope you can see that in the video. It was blue, and then it became green, and now it is sort of a greenish yellow. So I'm going to try to add just half a drop, if I can do that. Oh, that was one drop. Let's see if that works. One drop. What color do we get now? So it's turning blue as I mix it. As I mix it, there it goes. Oh, it's now green and a little faint yellow. Okay, but there's definitely lots of green there. So since it's in the process right now, it's at equilibrium, it's got a yellowish green color, then we must now be at a pH pretty close to the pK for bromothymol blue, because we have a greenish solution, a mixture of both the acid and base in roughly equal amounts. There's another small drop. Let's see if I can get it even a bit greener, or did that extra drop shift it even further to the right? And there we go. So that one more drop, you can see now it's, well, as I keep mixing, the blue is turning into a green color, so it's reaching equilibrium. There we go. So there's a definite green color. So this solution is now at a pH very close to the pK indicator for bromothymol blue. Add one more drop of sodium hydroxide, or about a couple more drops. So now, did you predict that this should cause the forward shift? And now we see the blue color definitely back again. So we can cause the equilibrium to shift forwards or backwards. If I were to add more of the acid, put a bit of squirt of acid in there. That's going to shift the equilibrium back to the yellow. If I were to add more base, take a big squirt of the hydroxide ions, that's going to shift the equilibrium back the other direction. So the indicator changing color is really just Le Chatelier's principle as we are changing the concentration of hydronium in the equilibrium mixture. So in this table we have a list of indicators, a more extensive list of indicators, and their color changes and the pK for the indicator. Remember that K indicator is simply the Ka for the acid version of the indicator. So when we look at bromothymol blue, the one we were just looking at a moment ago, we know that it changes color from yellow to blue, and we know that its pK indicator is 7.3. If you were to take 10 to the power of negative 7.3, that would give you the actual Ka for the indicator. So it would be very close to 10 to the negative 7 as the Ka for the indicator. Over on the side here, I have a table with those same indicators, and if I find bromothymol blue, here it is here, and we go up to the smudge of color, it shows yellow turning to blue, and it shows a bit of green right in the middle. We said that that green right in the middle is where it's changing color dramatically. Now, if you were to go from there over to the y-axis, you'll notice the pH at that point is just a little bit above 7. So when the color change is occurring for bromothymol blue, that color change is occurring at a pH very close to the bromothymol blue pK indicator value. All right, try and take a look at another one. So over here we have phenolphthalein, a common acid-base indicator in chemistry in high school. Going up to the color smudge, it looks white down here, which means it would be colorless at low pHs. And then above it, it's pink, so at high pHs, it will turn pink. And it's changing color oops, I just put a drop of water on my paper. It changes color. That's what happens when you think you have clean, dry pipettes. It changes color from colorless to pink at a pH just over pH 9. And when you look over at phenolphthalein in the list of acid-base indicators, its pK indicator was 9.5. So we expected phenolphthalein to change color at around pH 9.5. One more, we take a look at methyl red. Methyl red's pK indicator is 5, and it changes color from red to yellow. So with that information, we know that when we look over here at the table, we're going to see that methyl red is a red color below pH 5. It's a yellow color above pH 5, and it should be changing color from red to yellow when the pH is close to 5, the pK indicator for methyl red. So let's take a look at the table over here. Methyl red, it shows up here a reddish color becoming yellow. So that means at any pH below here it's red. At any pH above here it's going to be yellow. And that color change is happening very close to pH 5, which was the pK indicator for methyl red. So that's how the pK indicator, the pKa of the indicator, is connected to the color change that occurs for the indicator. All right, in this next part of the experiment, we're going to use those acid-base indicators to estimate pH of a solution. In this activity, I'm going to show you a well plate that looks like this with different acid-base indicators in each well. The indicators we're using today are crystal violet, thymol blue, bromophenol blue, methyl orange, bromocresol green, methyl red, bromothymol blue, phenol red, phenolphthalein, thymolphthalein, and alizarin yellow R, sometimes just called alizarin yellow. If you want, there's a QR code up here where if you have your cell phone, you could use that to scan this, and it will take you to a chart of indicators similar to the one we just saw that will show you the colors that each indicator has and the pH where they change color. So you want to have that, or if you have your own acid-base color chart, something like this, with a list of acid-base indicators on the side, pHs, and the colors where they change, the pHs where they change color, you could use your own table like that. So I've got a well plate already prepared, and in this well plate I've put 3 or 4 drops of each of those indicators into the appropriate wells. And now I'm going to take a solution of unknown pH, and we're going to put a few milliliters, 3 or 4 milliliters of this unknown solution into each of those wells. So I'm going to squirt a few milliliters in each well, and from the colors that you observe as we add this, you're going to try to interpret the color chart that you were seeing and estimate the pH of the unknown solution. Now, each of the unknown solutions that we're looking at today have whole number pH values. So their pHs are something like 2 or 4 or 8. They're not going to be pH values that are decimals like 8.23. So knowing that these are whole number pHs, can you use the colors that you see in the video to estimate the pH for each solution? So I'll reveal this one more time so you can see the indicators that are there. So the top row is crystal violet, thymol blue, bromothymol blue, methyl orange. You can see the colors. Brome cresol green, methyl red. It's a little faint, but it's a bit reddish. Bromothymol blue, phenol red, and then the bottom row of the dish, phenolphthalein, thymolphthalein, and alizarin yellow. Okay, the alizarin yellow here looks to be a faint yellow color. You may not be able to see that in the video. All right, so pause the video, try to figure out the pH of that unknown solution. Now I have several other dishes already prepared. So that was the first solution. Let's take a look at a second solution. So solution number 2. So above, I'm going to put the dish with the indicators showing, and below it you can see which indicators we were using. Right? So that is solution number 2. Pause the video and see if you can figure out the pH of solution number 2 based on the colors of those indicators. And now solution number 3. Okay, same idea. Solution number 3. You want to look at the colors you see, pause the video, compare these colors to the colors on your color chart, and see what you can deduce. There's some bubbles here, but it looks purple colored in that first dish, first well rather. All right, solution number 4. Can you use those colors and deduce the pH of the unknown solution? And finally, solution number 5, same idea. These are whole number pH values. Can you look at the colors you see in the dish and deduce the pH of the unknown solution? All right, so that was an introduction to acid-base indicators, their chemistry, and hopefully using them to estimate pH values successfully.